All right, everybody. So I hope you guys all brought the printout of this thing. That's the whole goal, is for you guys to print this out, even though you just went through the first page. If you're not, you can pull it up on your phone or something like that. But we're going to go through and do a little bit of math today. But most of it is to prove some or provide evidence, like data-driven evidence on some points about alkenes and their relative stability, and particularly what happens when alkenes are in relative proximity to each other. So we're going to have some key point takeaways today, but it's stuff that I want you guys to kind of work your way to based off of the data that we have today that is presented for you in this first part. So I went through and looked at all your bridges. For most of you, you got the right idea on number one. And this is something that's not new. What conclusions can we draw about the relative stability of alkenes based on their number of substituents? Going back to last semester, this was officially Zaitev's rule, but it doesn't really matter. The point is that when we look at these numbers, greater negative numbers mean what? More or less stable? Correct, less stable. Think of them starting off at a higher point, so they've got farther to go to get down to alkane. So an alkene with a very high potential energy is very unstable, and this number being negative means how much energy it gives off to go down to alkane. Everybody good on that? All right, so unsubstituted alkenes are very unstable relative to other alkenes. And then tetrasubstituted on the flip side at -111 are significantly more stable. And then they just kind of go in between. So what's the general conclusion you can draw about that? Yep. Perfect, exactly. So more substituents on an alkene makes them more stable. Fewer substituents on an alkene, less stable. That's it for number one. Does that make sense? Everybody, I think we all approach that in one way or another, but we'll write that down. More substituents on an alkene means that they are going to be more stable. All right, what would be more reactive? Yeah. So things that are more stable are less reactive. Things that are more reactive are less stable. Everybody good with that? So if you got multiple alkenes within a molecule, let's say I've got a molecule that has a monosubstituted at one end and a tetrasubstituted somewhere in the middle, which one of those two alkenes would you expect to react first? Yeah, exactly. The monosubstituted would react first because it's less stable, so it's more reactive. Everybody got that? Okay, good. All right, the second question I was asking you to kind of compare the relative stability of the disubstituted. So just focusing on these disubstituted alkenes right here, comparing them relative to each other, what conclusions can we draw about the stability of these different disubstituted alkenes? Which one's the most stable of the disubstituted alkenes? Yeah, the one right here in the middle. So how would we classify this substitution pattern versus this one? Yeah, exactly. So this is technically E, or trans, where the substituents are farther apart. And hopefully we remember going back, there are a lot of times that this has come up. Everything's comprised of electrons, and the more closer they are together, the less stable they are. So thinking about bond angles in small rings, more closer together, the less stable they are. Thinking about when we have dihedral angles and they're eclipsed, the more close together, the less stable they are, et cetera, et cetera, et cetera.
So for the top one between the middle, for the disubstitute, would that be 6? And then with one below it, would that be the geminal?
Yeah, so this one would be geminal because they're on the same carbon. This one doesn't come up nearly as much, but the idea is this one's kind of somewhere in the middle. But when you've got one substituent on each side, this comparison here is really important. And I know that the difference between 116 and 120 probably doesn't look like a huge gap, but it is relatively significant. And we do see that something like this would be what? More or less stable than that one.
So
Hold on. Is this one right here more or less stable less stable, so it would be more reactive. Yes, perfect. Okay, go ahead.
So I was gonna say, so that essentially the trends is based on the arteries. So,
Yep. So this would be cis or Z, and it is relatively less stable, just comparing these two. And the one right below it, which is trans, or E, would be relatively more stable. Does that make sense? Everybody following along? I hope the goal today is to take a lot of baby steps towards some pretty big conclusions eventually. So just keep following these little steps. It's a lot like acid base, where it's a lot of little steps, but it's hard. It's easy to get lost because there's just so many of them. All right, so far so good. So that's in effect the answer to 1B.
I was confused by the order, because then I like realized, because then it went from negative 120, then negative 160, then back to negative 120.
Yeah, so here, if you'd like to, I can give you the Word document and you can change it to however you want to.
Oh, I'm sorry.
But yeah, I know most of them are in declining order, but this one is not. But the main purpose here is just to
I
differentiate.
just didn't know if there was a reason for that. I was just
Well, these are the two most common ones, so I put them first, and then this one's a little bit more weird, so I just put it afterward.
Okay,
But you're right, it doesn't go exactly in order.
That makes sense to me
Okay.
now, okay.
All right. But the big, besides this one, which is really unstable, the gap between mono-substituted and tetra-substituted is not huge. So there is a very big difference between 15 kilojoules per mole, which is only really like, it's about 10% of all of this energy. So a difference between a gap of this and a gap of that is meaningful and appreciable and will definitely impact what goes first. All right, so this is new stuff. So let's move down here a little bit. So what would a reaction energy diagram look like? Angel, you remember what reaction energy diagrams look like?
Is it well, it ends up like.
Yeah.
The hills, yep.
So if this one is reacting and we add hydrogen, what molecule would this turn into? Well, just all we're doing is hydrogenation, yeah?
It was, the alkene was one into an alkane.
Perfect. So just alkene. Yeah, we just add hydrogens to both sides. It just turns into an alkene. All right. So Angel, would this go up in energy or down in energy? It would go one of those things.
It would go down.
It would, yeah. So the delta H for this reaction, specifically for this double bond. So looking at this double bond here, we can predict how much it'll go down in energy, because this is what? Gabriel Korn, mono, di, tri, tetra, unsubstituted alkene. Yes, and is it E or Z? E. So what is the value? Negative 116. Is that right? I believe you. Okay, negative 116 kilojoules per mole. All right, so again, the really important, this is negative. So yes, Angel, it would look like this. It would go down in energy. You would start at an alkene, which is relatively higher energy, and go down to an alkane, which is relatively lower. Everybody good with that? All right. Which part of this reaction energy diagram corresponds to the heat of hydrogenation? Avery. So where do we see that negative 116 kilojoules per mole? Where would that be exactly on this little diagram? Well, your change is negative 116 to get from where to where? Perfect. So it would be right here. It's the gap between where we started, yeah, and where we ended up. So this would be your delta H. This is going to be your negative 116 kilojoules per mole. So the point is really, and we don't have to worry perfectly about all of these numbers. I'm not going to ask you to regurgitate any of these numbers. You do not have to memorize any of these numbers. We're just going to use them to draw conclusions today. But the point is that it's going to go down in energy by a certain amount, and it's a pretty big gap. And that's where we would see this. Everybody good with that? Okay. If you had two alkenes, what would you expect to see? If one alkene goes down yay much, What about 2 alkenes? Yeah, it would start higher, right? And 5 alkenes in a molecule would start off even higher, right? So the more potential, more alkenes, you're adding more and more potential energy. Everybody go on that? Okay. All right. So, yep, in the same molecule. So here we go. New reaction. New molecule. I got 2 alkenes. All right, Alex, you ready? All right. So which of those would you expect to be more reactive and react first? The one right there where the mouse is. Yes, that was a coincidence. Why? All right, so let's put some numbers on these things. So this one right here would be, what's its heat of hydrogenation? You can just flip back, totally fine. Negative 120, great. And this one right here would be, yeah, good. All right. And so you're right. The one that would be most reactive or least stable would be this one right here. So that would be the one that we would expect to react first. All right. Kaylee, would you predict the heat of hydrogenation for this overall reaction here?
So since I'm gonna, so since the two would kind of be combined, right? Would you just add them together?
Yeah. So I didn't ask you to draw this, but if you think about like kind of a reaction energy diagram, we would do, one of them would go down by a certain amount, and then the second one would go down by a certain amount. And Alex already said the first one would be that minus 120. So we would see it would go down by minus 120, and then it'd go down by minus 116. And since Avery, your question was kind of about the gap, we basically just be adding these 2 gaps together, this gap and this gap. And so you're just combining them. So, yep. 236 kilojoules per mole. Go ahead.
So negative 120, like maybe 116, that is when it goes from being an alkene to an alkane?
Yep. Yeah, and so in this reaction overall, we've turned both of them into an alkane. So you would get the energy given off by both of them.
I didn't think that.
That's all right. Does that make sense?
Yeah.
Everybody following along here? Okay. Yeah, and so this is part of what we can do to predict relative energy of alkenes. So what we're doing at this point really is just considering them one at a time. But a big part of today is to kind of look at what happens when we have multiple alkenes put together.
Yeah, you know, right now, it might help.
All right, so Chase, what would be the heat of hydrogenation for a molecule with 2 mono unsubstituted alkenes? Right, so let's just say, how long do you want this thing to be? Can we do more than 4?
6.
Great. I'm not trying to be difficult. I'll tell you why in a minute. All right, so this one, this 6 carbons, great. You got 2, you just died 2 monosubstituted alkenes. So delta H is just going to be, each of those are negative 126, right? Yeah. And so we're just 2 times negative 126 is negative 252 kilojoules per mole. And that should be pretty much what we would expect. You're just adding those things together. And in this case, because it's 6 carbons long, there is no interaction between this double bond and this double bond. They're just both there. And so you just add them both together. And so what we see is that, that molecule, if you pick 5, they look exactly like this. It doesn't really matter. But the actual value for the heat of hydrogenation for this alkene is negative 253. We said negative 252. We're pretty much spot on. That's what we see when we put 2 of these things together. It's basically you just additive. Everybody okay with that? Taking that data and referring to this. Yay, great. All right, so Laura, talk to me about this beast right here. This is called accumulated diene.
So it's not as, okay, so the order, so the one at the bottom
Don't worry about the bottom one. Just compare this one right here, this cumulated diene, to the one that we just did. So this is called isolated. So the idea of isolated dienes is that they're just not right next to each other. They're not interacting with each other. They're both there. They just both exist. All right. But this cumulated, this is something that we have seen or drawn. Like a lot of folks try to draw a lot of these molecules way back when we were putting a bunch of double bonds in back at the beginning of the year, like back in EO1. And there's kind of this hanging like, well, we don't see these double bond, double bond, double bond and all in a row. It's not something we see, but this is why. What is this number telling us? This negative 295 compared to negative 253.
Since it's more negative, it's more reactive
Yes?
and it's less stable
Yes.
compared to, you said the isolated.
Yes.
Because the more negative it is, the more reactive.
Correct.
And then
But I want to point out the numbers here. This is 40 kilojoules per mole less stable than a normal diene.
that's a lot. That's a lot.
It is. So going back to our very first page, the difference between like mono substituted
Yeah.
and tetra substituted was only like 15 kilojoules per mole.
So that's huge.
This is a huge gap. You will never see these in nature. Why not? What did you just say?
Because the values it's too big. So
It's really, really,
reactive.
yes, which means that they're very, very
Unstable.
unstable. Yeah.
So they can't exist.
Yeah, so these things would do anything they could to react, so we actually never see them. Three-dimensionally, they're really weird. Three-dimensionally, what's the hybridization, Angel, of this carbon right here? Oh, gosh, hybridization. It is sp. So if you're sp, you have two leftover p orbitals. So what this thing, I'm gonna do my best. Don't judge me too harshly for this. What it would look like is that carbon in the middle would have one p orbital like this that would overlap with a double bond to the right, kind of doing this thing. And then it would also have a p orbital that it would be kind of coming out at you and going away. So it would interact kind of like that on the other side, and these things end up torqued to each other, so the double bonds end up perpendicular, and it really ends up being a very unstable molecule. And so that's why we don't see these. You can't buy a jar of these. You can't find these in nature. This is approximate because they don't last very long, and so they basically react on their own or react with anything because they're so unstable. So the point is, and we will never talk about these cumulated dienes again, because they're just really unstable. They basically practically don't exist. Like so many things, we can force them to exist for seconds in the lab, but they just react on their own, and they're more of a cautionary tale than anything. So when you're drawing molecules, don't pick to put two double bonds in a row. Just practically, it's just not a thing that we ever see or find.
So if we turn them into a lab, what would happen?
If you made these in lab, what would happen? They would probably react with water or oxygen or something and just go away. They're not going to explode, but they'll just react with something. Basically, they're just not going to stay that way. Yeah.
So it will change phases really quickly.
Yeah, it would react with something, anything it could get its hands on. So a lot of these things, like, we've talked about the pKa of an alkane. So a molecule like this, we can draw it. No, that's hard to see. Like a C- and basically methane. It just doesn't exist because we can't make it because it's too unstable. And if it did, it would react with literally anything that it came in contact with. And so it just wouldn't exist for very long. So these are, I don't want to say not real, but they're like unicorns. They're fun to believe in. They're fun to draw pictures of, but it may as well just be shooting sparkles out of its horn because it just doesn't
Unless
exist.
we're like that scientist who have like supernatural powers.
Sure. Yeah, if you're a scientist with supernatural power, by all means, play with cumulated dienes. But otherwise, they're just really, really unstable. All right, the significantly more impactful and meaningful thing is this one right here. So Gabriel Korn Jr., tell me, what's that?
Junior.
I don't know. I don't know your dad's name.
Where did that one come from?
I don't know. My head's kind of working today. I'm trying to spiral up, but it's not working great. So looking at these things, okay, so compared to this isolated diene, this is a conjugated diene. Conjugated is a term we've used before. We used it when basically talking about resonance. We used it when looking at specific alkenes or carbonyls in IR. Remember, they would show up 50 lower because they had kind of that resonance. They were conjugated. The whole idea of conjugated is when you have a double bond, single bond, double bond. That lets you move double bonds in resonance structures. So these things have, at least theoretically, resonance structures. They have this pattern of double bond, single bond, double bond. And that makes them, the term is conjugated. It's a term that's come up, but here we go. Conjugated dienes, dienes being just two. So this value here is -236. So what does that tell you compared to this isolated diene?
That's more stable.
More stable by how much? You can do it. 53 minus 36. Yeah, 17, yes. So basically, whenever you have a conjugated system, big picture without the numbers, they are what? More or less stable than isolated?
They're more stable than isolated.
Correct. This is one of our big takeaways for today. Conjugated dienes or trienes or tetraenes or whatever are going to be more stable than by themselves. We know that resonance makes things more stable, right? And this is evidence of that. Although if you try to draw a resonance structure of this, it doesn't come out great. If we try to draw a resonance structure here by moving those double bonds around, we would see that you get something like this, and both C minuses and C pluses are really unstable. So resonance doesn't really explain this, because the resonance structure for this is, that's not in my head, is it?
No, it's not.
Awesome. I don't know. Let's say fixing the roof, and we're hearing it through the ductwork. Are any of you seniors? You're a senior. Laura, come back and say hi sometime. Otherwise, guys, I'm looking forward to fall 2021 so much.
Do you think coronavirus and all this stuff will be done by next year?
Will it be gone from the earth? I doubt it, but hopefully we will.
Like maskless?
I hope you guys are all getting vaccines next week.
I thought.
Okay. They're tremendously unstable. All right, so accumulated dienes are tremendously unstable, and that's all we'll ever talk about. All right, but conjugated dienes, they are more stable than isolated dienes by how much? You said it, Gabe. Yeah, so that's an approximated number, but I would say by about 15 to 20, but let's just use that number plus 17. So at this point, we're just gonna say plus 17 kilojoules per mole, more stable due to that conjugation, that single bond, single bond thing. Everybody go with that? All right, so we're gonna apply some of these numbers and see what we get to these four molecules. All right, Avery, good news. You get to do our first one here. So we're gonna have 5 numbers here. Okay. So what is this thing right here? Uh-huh. You want more specific? Yep. So what's the number on a monosubstituted alkene? I wrote all these numbers. So Laura, you will get your chance. It's okay. You can do it on your own if you want to. Go, Avery. I'm ready. Okay. Uh-huh. Right. Okay. So furthermore, do you see that this is conjugated? We've got this double bond, single bond, double bond, single bond, double bond. So these conjugations, now we have 2 conjugations, 2 spots where these should be through resonance or whatever, they are more stable than they otherwise would be. And what do we add for each of those spots? Scroll it up. Yeah, so logically, it should be about plus 17 for each, because every time that you've got that conjugation, you're going to make this more and more stable. Everybody good with that?
It's only if there's double bond and single bond that we want.
Exactly, and that's perfect. This is probably, we got two really important takeaways from today. That's one of them.
So
That
that's
it's-
why it doesn't work with the first one.
Yes, it didn't matter for this one back here because this is an sp3 carbon, so it has 4 single bonds and there's no resonance. So there's a complete interruption of resonance. So it's not actually about resonance, but it is about those p orbitals. So if we were to draw out these p orbitals, we would see that there's p, and then you've got this interruption right here, and then there's p and p. So there's no interaction there. But in this conjugated system, we've got a p orbital and a p orbital, and then these also have p orbitals. So there's an extended cloud of p orbitals that goes across the entire molecule, and they can interact with each other, and that's where that stability comes from. Again, with the one that Chase drew, you got, it doesn't matter how big your gap is. If you have an interruption, there's an interruption. Interruption being something with 4 single bonds. So when you wanted to do 4, we get to a more complicated issue when we got 4 in a row because they become conjugated all of a sudden. So these would be conjugated all the way through. This is going to look a little bit more complicated now, but you see how you've got all of those interactions there. All right, so Avery, what's negative 126 plus 17 minus 116 plus 17 minus 126?
Are you serious?
No,
So,
I did it on a calculator this morning. You guys can always just type these things in. I trust that you guys could add these up if you wanted to, but this is what you would get. Everybody good with that? Negative 334? Okay.
If you'd asked me, and I said, I just wanted to.
Yeah, I should have held it up in my hand, negative 334, you'd be a genius. All right, everybody got that? Does that make sense how we would approach that? All right, so let's move on and look at them a little bit in rings, but it should be the same theory. Okay, we got a dye substituted. This is trans. So Alex, what would this one be? Great, and there's nothing else to that one. It's just one double bond. It turns out that it's not exactly 120 because there are some differences going on here. When you're in a ring, you have constraint, and so it's not perfect, but it's right around there, and that should hopefully make sense. So this is just one double bond. There is no conjugation because there are no other double bonds. Correct. Conjugation can only happen when you have a double bond and then a single bond and then another double bond. It's about the interaction between 2 double bonds. Yep. Yep. And so if there's a big gap between 2 double bonds, whether it's 1 carbon or 20 carbons in between, they're just isolated and they don't interact. But when it's double bond, single bond, double bond, they have this interaction that makes them more stable than normal. Okay. All right, so here we go. So I didn't put this one in here, but if we had a molecule like this, okay, what would you expect this one to be?
I'm gonna be honest, I'm gonna get a little flustered during this one.
Yeah, no problem. So let's, here, I'm going to, no, you guys won't be able to see this out in Zoom, but just imagine that it's not in a ring, it doesn't really matter. It's a double bond. We can just look back to our chart on the very first page. Yeah. Yeah, so if this molecule had 2 double bonds, and notice that they're not next to each other. So this is a double bond and then a single bond, but then there's another single bond before the double bond. So these are just isolated. So what would you expect the energy for this one to be? Perfect, yeah. So for this one, because they're isolated, we would expect like minus 120 and minus 120, and we would put that together and we'd say that in order to turn this into an alkane, our delta H would be negative 240. Everybody cool with that?
I'll jump ahead later. We haven't got there yet.
That's okay. All right, so you get to do this one. Don't we?
That's what I was wondering. Is that what the 17?
Yeah, hold on.
Okay, sorry.
All right, so Chase, let's do this one. So as opposed to our isolated dyeing, now we do have conjugation again, right? So what would you expect for this one? All right, so we get a negative 120 and a negative 120. But then this would be, you're basically looking at making it more stable. It'd be like a positive 17. It's okay. So thinking about this with kind of negative 240 plus 17. You can type it in. Yeah, kilojoules per mole. So that makes sense to everybody. That would be kind of our approximation on here. Once again, it's not precisely this because when you're in a ring, things are a little bit more complicated, but that's what we would roughly expect. Everybody go with those. See where those numbers are coming from. All right. And so we would expect for this one, we would basically see like loop, 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 because it would be 3 of these. This one would just be 1 double bond, so just go down once. This would be 2 double bonds, so go down and then down again. And this one here, we're back to 3 double bonds, so this is a conjugated triene. So Laura, talk us through this one. Good news.
It seems like this is a trend in the, so negative 120,
Yeah.
negative 120, negative 120. And then since it's in between, we know the trend would be plus 17, plus 17, and plus 17 between those values.
Right.
We would end up with negative 1. I probably calculated that all the way down.
So it'd be negative 360. And then 17 times 3 is 51, so plus 51. So it should come out based on that to be negative 309.
That's what I thought.
Okay, does that make sense to everybody? I know we went fast through that, but the idea is when you got 3 double bonds in a row, you'd have 2 spots for conjugation. But if you've got 3 double bonds in a ring, then you got 3 spots for that conjugation. All right, everybody feel comfortable with where we came up with these numbers? Okay. So the top of that last page is the actual measured values. So the first one, here, I'm going to put my correct answers in blue. The correct answer here is negative 335. How do we do? Great, everything is working. Fantastic. This one is negative 118. Yeah, so it's pretty close to what we would predict. This one is negative 230. Again, this is a little ways away than we would expect, but it's still, I mean, we're off by, our margin of error is 7, which is pretty small. So pretty good about that. All right, the actual value here is negative 206. So that's way, way, way far off. So and this is kind of our second main takeaway of today. When we go backwards, we had kind of hopefully 2 surprises. One is that when you've got double bonds that are conjugated to each other, there's something going on that makes them more stable than they otherwise would be. So it changes our math because of conjugation. When we have aromatic rings, specifically benzene, there is another, we already factored in our resonance, or our conjugation. So there's something even bigger and even way more meaningful than resonance going on that makes these things what? More or less stable than a normal triene. More stable by a lot. Remember when I was getting all crazy about how accumulated dienes are like 40 kilojoules per mole less stable than they should be, and that's a huge gap. This is 100. So this is benzene rings. I don't want to say the word magic, but they are ridiculously more stable than they have any business being. It took people a long time to try to figure out what the heck is going on with benzene rings. Benzene rings, do we see these in nature? Yeah. Yes, and we see not only benzene rings, but we see all kinds of these aromatic rings in nature all the time. DNA is just stacks of these aromatic rings. There are aromatic rings in many of your amino acids, so in all of your proteins. They're in all of your RNA and DNA. They're everywhere. These things are consistently found in nature all over the place because they are the most stable rings, and it's not even close. So yes, these things we do find all the time. They are naturally formed all the time. This is basically what graphite is. So if you're writing with a pencil, you're basically just smearing benzene rings all over your paper. But this is something that we find all the time. So Yes, it is all about molecular orbitals. And so my plan for the last week of the lab, because now we have an odd number of weeks of lab, so I can't do another in-person lab with half the lab there 1 week and half the lab there another week, is we will go through and I will try to help you guys navigate to the answers to these questions, because the same, it's complicated, and instead of trying to, like, in 50 minutes tell you exactly why this is, I'd rather spend some time kind of talking through and getting there. But molecular orbital theory is really great for explaining two things. One is why when you look outside, grass is green and flowers have colors. All of it is about organic molecules within those things. And it has to do with molecular orbital theory. The second is all of this craziness, resonance does not answer any of these questions. And so it's all about molecular orbital theory, which is something that you guys talked about a little bit in Gen Chem, but I'm expecting no one remembers it. So we will revisit it a little bit that very last week in lab. But for now, the takeaways are, our predictions were pretty good, but what can we say about the stability of benzene rings? Okay, let's be a little bit more specific and scientific. All right, not different, they're way, yes. So aromatic rings, benzene,
And so since they're more stable, they're less reactive.
absolutely, are significantly more stable than conjugated trienes would ever be, or isolated. They're significantly more stable. In fact, it results in this really weird looking reaction energy diagram. So I would like you guys to, so starting with this, when we hydrogenate this, we would hydrogenate one of the double bonds, which would actually give us this molecule, right? And then another of the double bonds, which would give us this molecule, and then another double bond, which would just give us cyclohexane. So take a stab at drawing out what the reaction energy diagram would look like when you go from benzene to cyclohexadiene to cyclohexene to cyclohexane.
Would we still use the same nomenclature as we did for 2 and
Yeah, you're still using the same values. But you actually have the values now. So here's your delta H's. Negative 206. It's okay. Yeah, but it's a little different now.
Yeah.
So you can kind of see where they are based on those numbers. Yeah, so what would be higher? This one or this one?
So as long as I switch the numbers around, the squiggles are right.
Most of your, these squiggles are good. I like think about those two values versus each other. Yeah, so there should be a bunch of humps, but
Just
that
switch
would
around the
last a little
values.
less.
I'm
So-
probably all the way wrong, but
So there should be multiple humps because we're looking at multiple different hydrogenations, right? So let's just put these values where they are. So this is going to be our 0, right? This is our baseline. All right. And this last one will be how much higher? We got the number. 118, right? Okay. So this would be, put that right there. So here is my cyclohexene, and this gap, this would be negative 118. Everybody cool with that? All right. So this one up here, the second one we got, this one had a gap of negative 230. So it's about, but not quite twice as high. So we would say that going, but still, negative 230 is a larger gap than negative 118. So this one would go down in energy, right, to get down there and then to get down here. Everybody good with that so far? All right, so this is the weird one. So this is negative 206. So where would this be relative to this energy level? It's not negative 206 to get to here. It's negative 206 to get all the way down to an alkane. Yeah, so this one would actually go up. So it turns out that benzene, because its heat of hydrogenation is negative 206, and all of these are compared to our final product, actually would have to go up in energy to react. So every other alkene has a heat of hydrogenation that's a negative value, meaning that you give off energy when you react alkenes. In other words, alkenes are less stable than alkanes, so we can react them pretty readily. You might remember last semester, we had a lot of reactions of alkenes. You could add something to either side. It's pretty easy to do. None of those reactions work on benzene. Because benzene, while it is double bonds, is not just 3 alkenes. The words of Avery, it's magical, right? But unlike every other alkene, even these conjugated alkenes that are extra stable, you can react them because they go down in energy. When you put some reagent with them, they will spontaneously react and go down in energy. That is not true for benzene. In order to react any one of these double bonds in benzene, you would be destroying its aromaticity, which would force it to go up in energy, which is not just a small gap, it actually is exactly the opposite direction than any of these other reactions. So benzene is super stable and super unreactive. And it's not just that it's less reactive than double bonds, it's almost reactive in the opposite way. It doesn't want to, it actively avoids reacting. So if you want to react a benzene ring, and so the only reactions we're going to do for the rest of this semester, we're going to look at polymers the very last week, but besides that, everything else for the next month is going to be about benzene rings and aromaticity. Is that aromatic rings are so stable, you need ridiculously strong, unstable things to react with them. So on their own, benzene rings are super stable and don't want to react with anything. And this is kind of the numerical evidence as to why. All right, any questions on that?
So you can, I'm trying to wrap my head around the orders of the numbers, because obviously it's negative 206. So it's not, so basically what you're saying, is it based on the bonds? Is why it goes first because
For right now, until Monday, just consider it just to be benzene. And yes, there's something about the nature of a ring that has conjugated double bonds all the way around, and specifically that has 3 conjugated double bonds all the way around, that makes it incredibly more stable than it has any business being.
So Monday we're going to go over why.
That's going to be a much longer conversation that we'll get to, but I'll give you more details. This is not the only benzene, the only aromatic ring in the world. Benzene is kind of our classic case, but there are a number of other aromatic rings. But it turns out that a ring like this is actually super, super unstable. And if you have 8 of them, it's super, super unstable. But then if you get to, you don't have to write any of this down. If you've got this 6-membered ring with 3 double bonds, it's really stable. And you've got this 4-membered ring with 2 double bonds, it's so unstable you basically can't make it. 8-membered ring with 4 double bonds, so unstable you basically can't make it. But a 10-membered ring with 5 double bonds, super, super stable. Yeah, so I'll give you more information on Monday, but for now, this is our test case is benzene. And benzene is going to be the most common one of all, by far. So that's the one that I want you to think back to as your classic aromatic ring. Okay, questions? All right, let's practice some problems. All right. All right, if I were to start with this molecule and add one equivalent of Br2, Angel, what would happen? Yep, why? Yep. Perfect. So this is a tri-substituted alkene, which would be more stable. This is a mono-substituted alkene, which is less stable. And so we would get a reaction. If you only had one equivalent of Br2, we would just get it over here. Fun fact, the mechanism for this is one that we did last semester. You're going to make a triangle and backside attack it. This is the reaction that is question number 1 in your lab that is due today. Okay. Don't react to benzene rings, just react to alkene in the middle. Okay. Does that make sense? Everybody good with that? All right. Ooh. Okay. Gabe, in the lab, do we need to draw how the yes, that is what the mechanism always means, the showing how the electrons move. So you need to show how the electrons move. I would be absolutely shocked if you guys have that mechanism memorized. Yes, you may resubmit. But basically for those questions about the mechanism, you guys are not being asked to do it from memory. You guys have your notes from last semester. The second question is about elimination. You should draw the mechanism, which is how the electrons move for that as well. But yeah, go back and hopefully you remember elimination E2, but if you don't, just go back and look it up in your notes from last semester. All right, which of these two molecules is more stable?
I would say no.
All right, don't take a guess. Talk it through, Gabe.
So the left one, that would be -230.
So don't sweat the math. Here's my guess. By next Wednesday, you won't remember any of those numbers, but that's okay. Angel, did you need your numbers to figure this one out? No. So this is a what? Disubstituted, trisubstituted, what?
Disubstituted.
Okay, so let's just do that. Okay, so this is disubstituted. What about that one? Right there.
That one's fine. No, it's trisubstituted.
Great. All right. All right, let's go over here.
Disubstituted.
Yep.
Disubstituted. And then trisubstituted.
Uh-huh. So there was one conclusion that you guys made before we even came to class, or I guess two, if you break out those disubstituted. But we know that when we can compare individual double bonds against each other, right? That's what Angel did. That's what we can do. That's what you're trying to do right now. That's what you could have done before you came to class today.
Yeah.
We added two more things today. One is benzene rings are magical.
Yeah.
What's the other thing?
The other thing was, the plus 17.
Right. Okay. I don't care if you remember that number. You need to know why that number was a thing, though.
Yeah, because it's conjugated.
Right.
So, it would be the first one, is the conjugation.
Perfect. This one is a conjugated diene. And this one will be an isolated diene. And so this one would be more stable by a good amount. With or without the numbers. That sound good? We got there? Everybody following? All right. Yes, sir.
So the one on the left is more stable, so the one on the right is, oh.
Yeah. It's more stable because it is conjugated. Conjugated will make any alkene more stable. Everybody good? Okay. Avery, which one of these is more stable? Yeah, why? Heck yeah. So this is a conjugated tetraene. This is a conjugated tetraene. But anytime you got benzene, it's going to make things way more stable. Everybody following all that? Okay. Those are our big trends for today. There are practice problems for today, but it all kind of fits into these buckets. I don't want to beleaguer any of these points, but how do you guys feel about this? Feel good? You can totally do this. All right. We are going to jump into some kind of conceptually more weird stuff on Monday, but my hope is that practice this, feel good about this, and get all these things right. Because today is, I hope, I mean, not that this was simple or intuitive, but that these are smaller takeaways. Monday's going to be a little bit more complicated, but take this home, practice this, be good with it, and get ready for Monday. Thank you guys very much. It's really good to see you all in person. I'll see you all sometime. Maybe in lab next week, maybe next Friday. I don't know. It'll be a surprise.